The difference between a good robot and a great robot often comes down to executing simple ideas incredibly well.
4 to 5.
Yep.
We've got a 4 to 5 reduction.
Yep.
And then we have an even bigger reduction from 10 teeth to 24.
Mm-hmm.
So
Okay,
we're
so that's
outputting
a pretty...
from 435, we're outputting like sub 300.
This robot from Team 23161, Cyberlist 76 in Romania, is a perfect example of that principle in action, packed with clever solutions that you can apply to your own designs in future seasons. I'm Coach Pratt. As a coach who's led teams to national championships and won multiple Inspire Awards, I've seen hundreds of robots, and I can tell you that the details on this machine are worth your attention. In this interview, we're going to run through their entire robot. We'll start with their incredibly solid CNC'd turret arm and the simple linkage that they use for their Outtake. We'll also get a great explanation of the tension their linear slides for the elevator and see their simple power takeoff system, PTO, and their level 3 hang, and how they're using a Limelight 3A to build driver automations that really make things simpler. Let's get into it. Tell me about your general strategy. What was your approach to this season?
This is our third robot of the season. First, we wanted to do more samples. Second, still samples, but we adapted the robot for specimens. Now, we try to do both equally as good.
Okay.
So, we have a triaxial turret that we use the most in autonomous, where you can pick samples from the sides. In Teleup, we only use it like a normal coaxial forward. Mm-hmm. Next, we have...
Sorry, with that turret, how are you actually rotating? You're using a geared input on that, or what is that?
We are using geared servos, axle servo here on the bottom. It's a 1-to-1 ratio with servo gears and pinions. Mm-hmm. We have an axle going through this metal plate held down by a shaft collar.
Okay.
Next is a Plex torque, geared 1-to-2, so 24 to 48. That does this, we call it Y motion.
Yep.
Next, we have the directly driven servo that tilts the claw and the claws.
Okay. Yep.
The architecture of the claw is...
why did you choose such a sharp angle?
When we do the transfer, when our claw picks up the sample, it needs time to fall down so that when the transfer happens, the sample is it's like all the way at the bottom. So when the strap transfer happens, we can pick it up from under. So we confirm that we always do the transfer.
Yep, that's great. That's great.
Next, we have the Outtake. Basic Misumi slider, counter sprung this side, stringing on this side with two strings for retraction. Yep. We have the spools down there.
Oh. Okay.
Now, the Outtake is an extension Outtake using a linkage servo that over-centers when it's closed.
Yep. Can I see that over-centered? I didn't actually get a chance to see that.
So when it's extended, we don't have an over-center, but when it's closed, it over-centers.
Okay, so closing is over-centered.
So that it doesn't budge or go open up by itself.
It extends out to grab the specimen, and then it places when it is back.
How it happens, retracted, it picks up the specimen, flips over, the sliders lift off, then it extends in autonomous. So we don't take as much time to drive closer to the chamber and back.
Okay.
So these extensions cuts a little bit of our driving time.
Yep. Nice. And you just have a little Misumi 220
220 sliders, to Misumi 220 sliders. Pretty much chained together by the shaft.
Yeah.
We are using 2 axle minis to rotate. One speed and one torque. Torque for the linkage, speed for the pivot, and the torque for the claw. This claw has an architecture that aligns our specimen so we can score with this horizontally.
And you're just saying the geometry of the claw allows you to align the specimen.
I don't have a specimen here.
That's okay. Yeah.
But the hook of the specimen sits somewhat like this. So we just have to push it into the bar and it clips on.
Yeah. Very cool. That's super slick. I really like that.
Okay.
Now, a thought for you. Why are you using a thicker diameter on this side and a thinner diameter on that side?
This is regular string.
Yep. Yeah, that's from the Go Build a Kit, I'm assuming, or
no,
like a Kevlar.
It's from Amazon.
Okay.
It's
a nylon piece.
Yes, dedicated for high power.
Yep.
And this is elastic Like
Okay.
we use it for counter stringing.
Oh,
So
you're
our
only
motor-
driving one side.
Yes.
And this is a retraction
Why
string
we
side.
do this? Because when you
yes.
string both sides, you
Yep.
can't string the string perfectly. You can tension it perfectly.
Yep.
You can't. You are human. You can't just tension it perfectly.
Okay, yeah.
So counter stringing on this side, which
Yep.
will help you
Yep.
keep all your sliders up
Mm.
when you are using the motor. So we take a little bit of the load of the motors.
Now, are you using 2 motors to drive this slide then?
Yes.
Okay.
2 Gobelin motors,
Yep. And what?
1150 RPM.
Okay, 2 of them, and they're just constrained on the same.
So 2 down there for the lift.
Yep.
And this is the one for the extender.
Okay. Yep. Yep. Beautiful. Okay, you just got some gears section that's pulling
Yes,
it all
it's
together.
a 1-to-1 ratio for
Yep.
both of them.
Okay.
We also have a dog clutch inside here. A dog clutch PTO mechanism.
Sorry, say that again. Oh, a PTO? Yeah.
PTO, a power takeoff mechanism.
Yeah, yep.
So this is a servo
Mhm.
that has a string
Mhm.
attached to 2 couplers.
Oh,
that-
way in there. Oh, okay, yeah.
It's kind of hard to film in there.
Yes.
But
I see that.
in there are 2 couplers that couple the drivetrain motors using gears.
Yes.
From the side, you can film the gears better.
Probably on the inside? Okay.
So we have a 4-to-5
Okay.
reduction.
Can I pop this plate out, or is
Actually, no. Oh, that one, yes.
Yes.
That one, yes.
Yeah,
I
yeah,
thought you
okay.
wanted to.
No, not the whole plate. Yeah. Okay, yeah, that makes it easier to see inside. So you're using this gear ends
So
up making
there's
that
a
power
gear
take off.
coupled to this
Yes.
pulley that
Yes, I see
is
that now.
coupled
Yes.
to the next.
Yep.
And there's an axle going through the whole robot.
Yep.
And inside here,
Mhm.
there are 2 pulleys. Kind of hard to film.
Yeah.
I'm not gonna lie.
Yeah, it's tough to get in
The
there,
belts
right?
are off right now because we are doing something for them.
Yes.
But
Okay.
a 10-to-24 pulley.
Mhm.
This gives us about almost 80 kilograms of pulling power when you are doing the level 3 hang.
Yeah.
How we
okay.
do the level 3
Yeah.
hang? We have 2 servos here in front of the robot that use string to push the robot
Oh, way down there.
up like this.
Oh, okay. Yeah. Yeah.
Then the sliders couple the PTO, they lift,
Mm-hmm.
attached to the bar, pull down, they get under these hooks.
Yep.
Then the bar of the hang
Mm-hmm.
rest on these hooks.
Mhm.
The lift goes back up. We balance the robot and we pull down for the level 3 hang.
That's awesome.
There's
Can you
an-
show me these little servos down here again?
So the servos
didn't-
are inside the plate, kind of
I
hard
can
to
see
film.
it back there, right?
With spools that
Yes.
I'm
I
gonna
just want to
lift.
see that little arm that pushes it
No.
down.
And when the servo spins using string, it goes down and back
That's
up
hilarious.
using springing to
Yeah.
help them come back.
What a great little idea. Great little idea.
We use 7 motors, 12 servos.
Yep.
We spend like almost a month on this card because we got a lot of experience throughout this year.
Mhm.
We are proud of what we're doing.
I would be. Oh, certainly.
Now we can talk about
Yeah, what kind
programming.
of interesting program do you have? Are you using any sort of camera vision? What are you using for
Please,
odometry?
Please. They know better.
All right, so we've got the Limelight 3A, obviously, and we use it together with our turret. This helps us basically find the optimal position to collect samples in autonomous.
Yep.
We only use it on autonomous because I think it's more efficient with enough driver practice to do well in teleop without it. And it's placed right here, if you want to zoom in.
Yep.
It's placed right on the claw. And
Yeah, I can see it. Right
exactly. At the start of the match, it'll extend like so. Grab, we use a neural network trained, it's an AI trained with a bunch of images of every single sample. And
Using
it'll just,
TensorFlow for that?
in the process, yes. And basically, it'll scan. We can set which one to pick up. It could be the closest, farthest, leftmost, rightmost. It'll determine the position, and then it'll zone in on it. Afterwards, we'll just do the transfer and keep going.
And how reliably have you got that working in autonomous?
In autonomous, almost 100%. Picks up almost every single time.
Great.
And for specimen auto, at least, it's even more efficient because we don't actually rely on a transfer.
Yeah.
We just bring it and drop it to the side. And we found that to be extremely efficient.
Yep.
And I guess we use that in a later part of our auto just because we liked how well it worked.
Very cool.
Yeah.
Anything else? What are you using for your pathing? It looks like you've got a
Pathing?
geometry pod
Of
down
course.
there. Are you using
let me flip-
pinpoint?
okay,
or-
stop this. No, We do not have a pinpoint. We just use a 3-wheel odometry, but we found that to be pretty functional. Although maybe a pinpoint in the future, we're not sure.
Yeah.
We use a Pedro pathing, and it helps us do pretty consistent trajectories.
Great.
It's worked for us so far.
Yep. Yeah, it's always interesting whether teams decide to use Pedro pathing or
it's something pretty recent.
Yes.
I mean, recent. It's been almost a year, I think. Well,
That's pretty recent.
We've hooked on it. We've hooked up on it from the start, and we really enjoy it.
Excellent.
Other than that, we have a couple automations for the drivers. Obviously, me and my twin brother.
Yep.
We use almost not all the buttons. To be honest, we try to keep it as low profile as possible, as simple, because the last thing you want in a match is to start fumbling around your buttons, start messing up. So we use like buttons for multiple tasks. We use the joysticks for separate commands. For example, if I point the joystick up, it'll go to a high basket. If I go down, it'll go to a low basket. And I can pick transfers too. I can pick whether to do a sample transfer or a specimen one.
Yep.
And with enough practice, it's become pretty efficient. We're proud of it.
Good. Yeah, that's my question is, what are you most proud of on this robot?
Most proud of? I'd say, because I'm one of the programmers, the vision, obviously, the inverse kinematics and all the work behind it. But the PTO, we're pretty proud of that too, just because it's worked almost every single time. We've had very few problems with it. And it's consistent, it's simple, it's lightweight, it's very efficient. We're proud of that too.
And you're using 435 motors for your drivetrain, I'm assuming?
Yeah, for the drivetrain.
A 1-to-1 ratio?
No, we've got 2 ratios actually that make up the transfer. PTO first.
Oh, the PTO makes sense, but I'm saying this is a 1-to-1.
This is 1-to-1.
Yeah.
And here we've got a 4-to-5.
Yep.
We've got a 4-to-5 reduction.
Yep.
And then we have an even bigger reduction from 10 teeth to 24.
Mm-hmm.
So we're
that's
outputting from 435, we're outputting like sub 300.
You were saying about 80 kilograms of torque earlier, yes?
Yeah, exactly.
Yeah.
Like
and how heavy is your robot in total?
It's almost 15. It's about 15 kilograms, yeah.
15, okay. Awesome. Well, thank you for sharing, guys. That's really cool. You should be super proud of that.
Yeah.